Hi everyone, my name is Jasmine and I'm one of the undergraduate teaching assistants for this course. In today's video, we're going to be going over cumulative distribution functions and probability density functions. We're going to be working with some Star Wars data sets. I saw in Yellow Dig that a lot of you like The Mandalorian, so I tried to find Mandalorian specific data, but the closest I was able to get was just overall general Star Wars data. So yeah, our agenda for today. We're going to be going over probability in general as a proportion as well as probability as a function, looking at the probability density function and cumulative distribution function. Our other TA, Paul, found a great tool in Wolfram Alpha that allows you to connect the CDF and PDF. So we're going to be looking into that, as well as Matlab. Dr. Middleton has a great tutorial posted in Module 4 under probability distributions that goes over a lot of different types of distributions in addition to the normal distribution, which we're going to be looking over today. So definitely check all those out. For whatever reason, if you don't understand any of the concepts I cover, or just want a different perspective, or maybe just a different way of explaining things, I did list different page numbers and lecture videos that you can look over. That way, if you're not quite clear still, you can look at these examples. If you want to find the Wolfram Alpha tool, I just recommend Google searching this, or I plan to post these slides too as well. So once I post the slides, you can just click the link and then follow it. And then finally, if you want more examples for whatever reason, it's not clear, or you just want to have some practice material, there's a ton of study problems at the end of chapter 4 that are pretty easy to follow along with. And you can post in Yellow Dig if you need help with them or come to office hours. So without further ado, what is probability? So this is something that we probably all have a general understanding of, but maybe it would be a good idea to just clarify and make sure we all are on the same page. So probability is a measure of the likelihood that any event chosen at random will have a given value. And in this case, event is just a general fancy way of saying an instance of a phenomenon. So an event could, for example, be tossing a coin, or the phenomenon could be tossing a coin, and an event could be getting heads or tails. So for example, the probability of the event of getting tails would be the number of events of tails over the total number of events. So it would be 1 over 2, because there's 2 outcomes when you flip a coin, unless you count it falling on its side, but that's really small compared to the probability that it lands heads or tails. So we're just going to say it would be 1 over 2. So P of tails would be 1 over 2, or 50%. We can also look at probability not only as a proportion, but we can look at it through this probability density function. So basically what the density function does is it assigns a probability P of x to every value of the random variable x. So in this case, we have our continuous variable of age. And so for each age value, so for each x equals a certain age, so x equals 20, there's a corresponding probability value on this red PDF curve. And so if we were to say P of x equals 20 for this specific population, you just go over and see that this is the probability corresponding to a person being exactly 20 years old. Now, the probability density function has a couple conditions. So for a function to be a probability density function, it has to be positive for all values of x. So this kind of is intuitive because you can't have negative probabilities. You can have a probability equal to 0, but you can't have something have a negative probability, just like you can't have a probability that's greater than 100. And then furthermore, the total area under the curve of this red curve would be the sum of the probability of each event occurring. It should add up to 100%, because if you add up the sum of all the probabilities of each event occurring, that's going to ultimately equal your total number of events. So for example, in our coin toss, if we said P of heads plus P of tails, it would be 1/2 plus 1/2, and that would equal 1, because the total number of events of x, which would be heads or tails, would be equal to the total number of events in the first place. So that would equal 1. Now, ideally, all of our data would be continuous. That would allow us to integrate over this function. And just to clarify, so this integral, that's not the PDF, that's actually the CDF. what is the PDF is this red curve. But it's important that the PDF is continuous. It's ideal because if the PDF is continuous, then we can integrate over it and find the CDF. However, for discrete data, so remember back to the first couple chapters at discrete versus continuous data. Discrete data is data that we don't have for each data point. So it could be categorical. So it could be like types of fruit, like apples, oranges, bananas, so on. Or it could be numerical, but just have some data missing in between data points. So what I'm talking about is for discrete data, for example, you would just have probabilities for certain values. You wouldn't have a probability in between 2 or 3. So an example of a data set for which this might be the case would be if I sampled all of you that are watching this video and I asked you how many classes you're taking. You can take half a credit, but you can't take half a class. You have to be, class is an integer. So number of classes you're taking, you can't take 2.5. So we'd have a probability. So maybe I sample 16 of you and there's one person that's taking 2 classes and maybe 4 people are taking 5 classes. And so the probability is corresponding to each of these different values, but we don't have anything in between. So that's an example of how data can be numerical, but still not continuous. It's still discrete. However, we can treat this basically the same way. So for probability mass functions with discrete data, we can treat it basically the same way as we do for continuous data with probability density functions. If you add up the sum of all these probabilities, similar to how we take the integral or the area under the curve, the total of all the probabilities, if you add this up, 1 plus 2 plus 3 plus 4, so on, that's going to equal 16 over 16. Same thing here, if you added up all the area under the curve, that would equal 1. The difference is that you're just using a summation notation versus an integral definition. So that's the only difference between probability mass and probability density. One has discrete data, one has continuous data, but you can basically look at them the same way for the purposes of this class. So why I was saying that it's really ideal to have a continuous data set and to be able to have a PDF that's integrable, or I don't know if I'm saying that right, but you're able to take an integral over it, is because that will help define your cumulative distribution function. So the CDF is the integral of the PDF. And basically what we're doing is we're assigning a sum of probabilities in the PDF. So sum of probabilities, that's your area under the curve. So for X equals a certain event, what is the cumulative probability from 0 to that value? So for example, if we look at our red PDF curve, if we were to say, what is the cumulative probability of having our data fall within the mean plus or minus 1? So if we're to say that we're looking between 0 and 1, the lower bound of 0 and the upper bound of 1, you would draw a line up here. So let's say that this is 1. Draw a line up here. Let's say it's around 0.8. Now you're using the fundamental theorem of calculus to look at these 2 points. So around 0.8 minus 0.5-ish, yeah, 0.5. Then that's what the cumulative probability would be between those 2 points. It'll be 0.8 minus 0.5. Let me show you what I'm talking about. I don't know if there. So if you remember back to Calc 1 or whenever this was covered, this integral would be like our CDF. So our CDF, if we take our upper bounds and the lower bounds, then you can just say, all right, sorry, no, this would be like our PDF. This is like our CDF. If you see like the CDF value at a certain point minus the CDF value at another point, that's going to tell you the area under the curve. So going back to the slide, if you wanted to know the cumulative probability from 0 to 1, it would be the CDF value at that point minus the CDF value at your lower endpoint. If we were to just say the cumulative probability of everything up until 1, then that would be 0.8. And that's why the CDF there is 0.8. Because everything, if you add up the sum of all of the area underneath everything from here into 1, it would be 0.8. Or approximately 0.8. The CDF has an S shape. That's because it has a lower asymptote of 0. Remember, we talked about how we can't have negative probabilities, and the upper asymptote of 1 because we also talked about how you can't have a probability above 100%. And the point of inflection, or the place where everything changes curvature, is at 0.5, which in this case, or sorry, yeah, 0.5, which is in course, like it corresponds with the mean. So if you, we're later going to be doing the inverse cumulative distribution function, but if you were to say, where is the probability equal to 0.5, it would be at the mean because it's centered, it's symmetric. So I know it's all a bit difficult to visualize, and I was kind of rambling too, but hopefully this Wolfram Alpha demonstration will help you better conceptualize it. So we're going to be doing it for Star Wars height data. So I was able to find some Star Wars data on Kaggle, and I decided to use height because it was the easiest one. Mass turned out kind of funny, but it was the one that seemed to follow the closest to like a normal distribution. And so for the height data, I went ahead and I calculated the mean and the standard deviation of all of these different Star Wars characters' heights. And the average was about 174 centimeters. Standard deviation was about 35 centimeters. And so for each of these characters, we can evaluate like where they'd fall on that distribution. So here's the tool. We can expand the controls right here. So our mean was 174 centimeters, and then the standard deviation was 35. And this lower and upper bound is going to depend on what question you're asking. So let's say we're asking the question of the same question as last time, the same question as I gave the example of, but for this data set. So let's say we're saying, what is the cumulative probability of falling between the mean of the Star Wars characters and within one standard deviation? So the mean plus one standard deviation. And that might take a second to load. I have it sort of loaded in some other, it's having a hard time loading there too, I guess. But maybe I can, once this loads, I'll post a screenshot and just put it in the slideshow. That way, when you watch this video, you can go back and see it, because I'm not really sure when this will load. But basically, the point of me showing you this is that to show you that the lower bounds of the PDF corresponds to the lower bound of this area under the curve, the integral, corresponds to the point on the CDF that you're evaluating as the lower bound, and then the upper point corresponds to the upper point. So you can see that this area could also be determined by subtracting this value around 0.8 minus this value of around 0.5. And we're going to see that in Matlab too as well. So moving on to our Matlab functions, we're going to be using 3 main functions today. Don't worry if you're not super proficient in Matlab, I'm going to be walking through everything. But basically, we're going to be using norm PDF, which returns values of the PDF corresponding to X. So for a certain X value, what is the probability of it being exactly that X value, as well as the norm CDF. So for a certain X value, what is the probability, the cumulative probability between 0 and that probability value. And in our example case, in this case, 0 is the mean. In our Star Wars data case, 0 is not the mean. So we're going to be having to use the fundamental theorem of calculus to determine the cumulative probability between our mean, which was 174, and whatever we decide to evaluate it at. And then finally, ICDF, that's what I was saying was like the inverse cumulative distribution function. So for that one, you give Matlab a probability value. So you give it 0.75 and it returns the X value that would be like the 75th percentile. So let's go ahead and demonstrate that. So here's the Matlab code that I wrote up. This is all going to be shared with you. I'm just going to be walking through it, not line for line, but explaining to you the main points and working in this command window so that it can be more interactive. But the first thing I did in this section was, if we run it, it's just going to import data. So I downloaded that data from Kaggle. It's all open source, so you can also download the same data. But I just downloaded this and I put it in Excel, and then I was able to import it here. I'm also going to be sharing this data set with you. And after you import data, there were a lot of missing heights. So if we go back here, if you scroll down, you start getting some people that don't have heights at NA, and Matlab doesn't know how to read that. So what we did was we just removed all of the missing height data. You probably won't have to do that for any of your data in this course, but for this particular data set, there were some that were missing. And then I went ahead and I looked at, okay, after we remove the missing data, how many characters are we actually sampling? 81. And what is the average height for that group and the standard deviation for that group? And so when we run it, we get 174 and around 35, which is exactly what we were plugging into Wolfram Alpha. So first of all, starting with the norm PDF. So I'm not going to read all over all of this. By the way, if you want better documentation for all of this, this is kind of just like a summary. But you can really just look at MATLAB's Help Center, and you can look up like norm PDF. So if you're ever stuck on anything, you can just go through and see how MATLAB has described it. They'll tell you like the inputs and the outputs like I have, just in much more detail. So for norm PDF, let's start out by asking the same question that we were in Wolfram Alpha. Or I guess this isn't the same question. Let's ask a new question. So what is the probability of having a character that's exactly my height? So I'm around 5'7", which is around 170 centimeters. And so if we were to set x equals 170, and we were to say probability equals, or we can just say norm PDF. And remember, we had saved our mean and standard deviation as mu and sigma. So MATLAB already knows what those values are. Now, this is returning the probability that if we have a character in the Star Wars universe, that they're exactly 5'7" or 170 centimeters. And it's a pretty low probability, even though 170 centimeters is pretty close to the mean, which is 174. And the reason why that is because you're looking at the exact data point of 170 centimeters. So at just that data point, what's the probability? And it's about 1%. We can also use the PDF function to create a plot of the PDF values themselves. So X takes either a number or a vector as an input. In this case, it's a vector. For those of you that might need a bit of like catch up on like MATLAB, basically what this line is saying is it's just saying create a vector from this lower bound with step size of this. So the middle is step size to this upper bound. So the lower bound I chose was -3 standard deviations. I figured that would give us a good size to look at the PDF. Step size is 0.1. It's pretty small compared to the numbers we're looking at. You could probably make it more refined. And then the upper bound is the mean plus 3 standard deviations. So this creates that X vector. And now we can say P equals norm PDF X mu sigma. So what we're doing here is we're evaluating the probability at each of these X values, and X corresponds to this vector. Ooh, and I didn't put a semicolon, so it really gave us the full thing. But the next thing we would do is we would say plot X and P. And there's our PDF for function. We can see it's centered around 174, and the standard deviation is around 35. So going forward to the CDF, the norm CDF, remember that CDF, we're looking at the cumulative probability. So remember how I was saying that there's an extremely low likelihood that someone is exactly 170 centimeters. What the CDF allows you to do is look at the integral under this curve, so the sum of probabilities for a given boundary. So let's start off with saying, what is the cumulative probability of having a character's height fall below the mean? So in that case, X equals mu, so X equals 174. And what is the sum of all of the area under the curve below the mean? So what we would do, because Matlab is integrating between like the lower boundary of like negative infinity or like really far out 0, I think it's 0. I'll have to double check on that actually, it's probably in the documentation, but basically it's integrating from some lower boundary to this x right here. Then that's going to return the cumulative probability or area under the curve of this PDF. So let's go ahead and run that. So x equals mu, and then cumulative, just copy and paste it, it's faster. So as expected, that's 0.5. And the reason why it's 0.5 is because we chose x to be our mean. And remember that it's symmetric about the mean. So half of all of the outcomes are going to be below the mean and half of all the outcomes are going to be above the mean. So it makes sense that our cumulative probability is 0.5. Now, what if we wanted to say, what is the cumulative probability of having a character's height fall within 1 standard deviation of the mean? So from the mean to 1 standard deviation above it. Now we can say x equals mu plus sigma. And then the cumulative probability minus 0.5. And the reason why it's minus 0.5 is because we're saying that we're looking at the cumulative probability from the lower boundary to around 209. That's what this is saying. So within, yeah, the x value is mu plus sigma, somewhere over here, and then minus the value here of the integral from 0, or from, I need to stop saying 0, but the lower boundary to the mean. So that would give us the area over here. Remember the fundamental theorem of calculus. So that would be about 0.34, so about 35% that you're within 1 standard deviation between the mean and 1 standard deviation. We can also do that for just random boundaries. We don't have to use like means and standard deviations. So if we go back at our data set, went ahead a little bit, but Princess Leia is 150 centimeters, and I don't know, she was like, I don't know, I wouldn't say she's my favorite character, but like I picked her because she's one of the only girls. So I was like, how do I compare to Princess Leia's height? And so if we compared my height to Princess Leia's height, we could use this as a vector. So we can use our x input as a vector. This is Princess Leia's height, this is my height. And we can evaluate the CDF of these values. So notice that C is returning a vector. That's because we had a vector input. So this is the cumulative probability from the lower bound to 150. So somewhere over here, that's the area under this curve. And then this is the cumulative probability from the lower bound to my height, which is like 170. And then by subtracting the two, we can find the cumulative probability. So this would be C2 minus C1. And that's the cumulative probability of someone having a height between my height and Princess Leia's height is like 20%. And then finally, just like we did for the PDF, you can plot CDF values. So let's go ahead and do the same thing. Not make the mistake of forgetting the semicolon this time. Did not want to run. Let's try again. There we go. So we have our nice S-shaped curve, which fits with what we've been talking about. So for example, if we're going to look at around 170, I'm going to try my best to get close to 170. Oh, it's 180. No. Okay, that's around 170. So that's at around 0.46. So that's our 0.45 value. And then for Princess Leia's height of 150, it's around 0.24. Yeah, 0.2. So that's why we subtracted these two points. This is our CDF plot. So moving on, the last function we're going to cover is ICDF. So sometimes it's helpful to be able to plug in a probability value and then see what is the corresponding X value. So this helps you figure out like percentiles, like the 25th percentile, 75th percentile. So for example, let's say that we're looking at p equals 0.5, which remember should correspond to the mean. If we say X equals, I don't know why I said this was X. It doesn't really matter, but let's look at that. Then it returns 174, which is equal to the mean, because that's what the distribution is centered around. So if we looked at 0.5, that's our point of inflection on this. Oh, I closed the plot, but that will be the point of inflection on the CDF plot. And then finally, we can also just take a vector of all these values. So let's say probability equals 0, 0.25, 0.5, 0.75. Now we can go ahead and run the ICDF and notice that we have this first one corresponding to negative infinity. That's because there's a ton of values that are going to give you a probability of 0. There's also a ton of values that are going to give you a probability of 100% or over, and that's why these are infinite. And then as for the 0.25 and 0.75, these like 25th and 75th percentiles, this would let you know like Princess Leia's 150, so she's like around the 25th percentile. And then this is, of course, our mean, because that's the same thing as above, just in this larger vector. And then someone in the 75th percentile would be around 197 centimeters. So I challenge you, after you watch this video, go back and just figure out your height in centimeters. You can plug it into Wolfram Alpha and get like the visualization, as well as see in Matlab, like, where do you fall under this distribution? If you were to insert yourself into the Star Wars universe, would you feel short or tall? You can look through and see. And something I missed is for ICDF, these two were specifically for the normal distribution, but ICDF, you can input a ton of different distributions. If we go back to our Matlab documentation, ICDF, there's a whole table of values somewhere over here. Yeah, there's a whole table of different probability distributions. So some of the ones that we're going to cover in this class are the F distribution, hybrid geometric, binomial, but for now you'd put normal. And each of these different distributions has different parameters that it wants you to input. So for normal distribution, it's going to be the mean and the standard deviation. If we look at binomial, the two would be the number of trials and the probability of success for each trial. So that's why up here it leaves it really broad and just gives you different numbers of parameters and different parameters. You have to match these A and B to whatever it says in the table for the distribution you're looking under, if that makes sense. So that's about it for our Matlab tutorial. I'm going to be posting this code so that all of you can look at it and play around with it on your own time. You could also totally play around with the different other column vectors. So like you could play around with their weight. I think that's the only other numerical data set in here. Could be wrong. I guess you could also look at the year they're born, but the rest of them are all kind of categorical data, so that would be a bit difficult to look at. But to finish up, if for whatever reason something I said didn't make sense, I know some of it was a bit like rambly. Hopefully some of it helped, but if anything didn't make sense, please come to our office hours. I haven't had anyone in my office hours so far. It's been kind of sad. It's just been me on Zoom, all alone. So Paul has office hours on Mondays from 10:30 to 11:30. Dr. Middleton has office hours Tuesdays and Thursdays from 10 to 11:30. And then my office hours are on Wednesdays from 10:30 to 11:30. All of the Zoom links are posted on Canvas. Please come and ask if you need help, or totally feel free to post in Yellow Dig. And then your other classmates can help you too as well. If you made it this far and you watched the entire video, thank you so much, because I'm pretty sure it's been kind of a long video. I don't know how long yet, but I guess we'll see. If you have any questions, like I said, come to office hours. I'm going to be posting all the content that I covered. Totally feel free to email me too. Here's my email. And yeah, I hope this helped you better understand PDF and CDF, hopefully in a more fun way using the Star Wars data than it would if we just use random numbers. But yeah, thank you. Have a nice day.